Hi, this is Ms. Fitzmaurice, and this video is an explanation of the problem on page 14 of your Unit 4 packet, okay, and it should say 2001 B2, meaning it was on the 2001 exam. What I want you to do before you watch the rest of this video is make sure you read and annotate the problem, okay, and then choose an equation or a topic. Then try to solve, and then watch the video to grade yourself. Okay, so now that you have watched this problem, let's think about the physical situation. And actually, before I go through the whole problem, I'm going to go through parts A through D and just explain what it is that you need to do. Okay, so we have this ball. We know that it has a mass of 0.1 kilograms. Okay, and it goes into this other ball, which has a mass of 0.5 kilograms. Okay, they're going to fly off the table, and so that's our basic situation. Okay. More specifically, it says that our first ball is moving with the speed of 1.4 meters per second, and it makes a head-on collision with target ball B at rest at the edge of the table. And as a result of the collision, we want to calculate the speed of the second ball. Okay, so the word collision and the fact that we kind of have a before and after picture and we have to calculate the speed should tell us that we need to use conservation of momentum in part A. So we have mv of each ball before and afterwards. In part B, it says the tabletop is 1.2 meters above a level horizontal floor. The target ball is projected horizontally. So that word projected should sort of clue you in that you need to think about 2D kinematics. And in part B, it wants to know the horizontal displacement, so it's asking you to calculate xx. Alright, so if it's asking you to calculate xx and you know that this thing is projected horizontally, you can probably get the idea that it's a 2D kinematics problem, and that what you need to do is set up an XY chart and solve for time. Eventually, you're going to use the Y to solve for time and put into the X. Okay? So maybe we're not quite to which equation we need to use. We need to list out the variables that we have, but that's the general strategy that we're going to take on. Alright, so then it says, in another experiment on the same table, okay, so we know that it has to be the same height, target ball B is replaced by a different target ball C with a different mass. So this is our new picture. Okay, we have two different balls. They don't hit head on, and so we have C kind of goes off at an angle, and we know that it strikes the floor a certain distance, 1.5 or 0.15, excuse me, meters from the table. Okay, and we know that the angle is about 30 degrees. Okay, so in C we want to calculate the speed of ball C right after the collision. Okay, looking and picturing this picture, you might be tempted to use 2D kinematics, but actually, you might be tempted to use 2D momentum, but actually since you know this distance that it lands on the floor, so you know it's xx, you can calculate the speed using 2D kinematics. So in C, you're going to do another 2D kinematics. Okay, this time you know XX, and so you're going to use your X information or actually you're still going to use your Y information to find time, and then you're going to put it into your X equation. Okay, in part D it asks for the Y component of the incident ball A's momentum right after the collision. Okay, so for that, you know, it's right after the collision. What we're going to use is sigma p naught y equals sigma p y. Okay, so that's the basic idea. Those are the things you're going to use. Now let's go ahead and actually solve the problem. And if you haven't already or you solved these incorrectly, you might want to go back and try to do it yourself. All right, so in part A, again, we want the speed of the second ball right after the collision. Okay, so we have our two balls. I'm going to name this one A and this one B, and we want VB after the collision. Okay, so we can go ahead and use sigma P naught equals sigma P. Okay, at the beginning, we have MA times V naught A. We know that this V naught, that's 1.4. And ball B is not moving, so it doesn't have any speed, so we have plus 0 is equal to, and then at the end, we know that A rebounds. Okay, so our after picture, we have ball B is flying off of the table, B rebounds in the other direction, or sorry, A rebounds in the other direction, so we have MA, VA, and it tells us a number for that. Okay, it tells us that it's 0.7, but remember it's going backwards, so we have negative 0.7 plus MB VB, and we're trying to solve for VB. Okay, so we have the masses of the balls, we have the velocities, now we just need to plug in the numbers. Okay, so MA is 0.1 times 1.4, and that's equal to 0.1 times negative 0.7 plus 0.5, the mass of the second ball, times VB, which we don't know. Okay, so we get 0.14 is equal to negative 0.07 plus 0.5 VB. Okay, I can bring this to the other side, and I get 0.21 is equal to 0.5 VB, and I find that VB is equal to 0.42 meters per second. Okay, so that was part A. In part B, we want to know the horizontal displacement, okay, and that's really of ball B as it flies through the air. So we're asking for XX. Okay, we know from part A that the velocity, and this is in the X direction at the beginning, I'm going to put VB naught X is 0.42. So we have VB naught X, and I'm just going to say VOX is equal to 0.42. And I'm going to make my XY chart, so I have X naught X is equal to 0, XX is what I'm looking for, my final horizontal displacement. V naught X, of course, is 0.42. Vx will also be 0.42 because our acceleration is 0. Okay, in the y direction, we know the height of the table is 1.2 meters, so x naught y is 1.2, that's our initial height. The ball lands on the ground, so its final height has to be 0. Because this thing is projected, it's rolling straight off of the table, v naught y is 0. Okay, it's not moving up and down at this initial point right here. We don't know Vy, but we probably won't need it. And we know Ay is equal to negative 10. Okay, so again, we're going to use this y information, to solve for time. So I'm going to go ahead, and to find time, I'm going to use x naught y, or xy equals x naught y plus v naught y t plus 1/2 ay t squared. Okay, so in our x naught y will be 1.2, xy will be 0, so that goes away, v naught y also goes away, and so I have 0 equals 1.2 plus 1/2 times -10 t squared. Okay, I can move these to the other side, and I end up with 1.2 divided by 5 is equal to t squared. All right, and you get t is about 0.49 seconds. Then to find xx, of course, you're going to plug it into the first equation again, and you end up with xx equals x naught x, which is 0, so I didn't put it in, but v naught xt plus 1/2 ax t squared. Okay, of course, ax is 0, so that term goes away, and we have xx is equal to v naught x, which we know is 0.42, times 0.49, our time, and we end up with about 0.2 meters. Okay, maybe 0.21. All right, so in part C, we're dealing with a totally different situation, and I'm going to redraw the picture very quickly. I'm going to pause it, and the picture is going to appear. All right, and we know that ball C gets hit by ball B, and it flies 1.5 meters away from the table. Now, the fact that it flies off at this angle of 30 degrees, it's still moving from side to side, so we don't really care about that in part C because we're just doing 2D kinematics. This is like a top-down view. And so we're going to set up our 2D kinematics information. We have x and y. X naught x we can set equal to 0. Xx is 1.5 because they gave us that. V naught x, I believe, is what we are looking for. Okay, because it's not going to be moving up and down at the beginning. V naught y is 0. X, y, the final height is 0, and x naught y is, of course, the height of the table. It's the same table, so it's still 1.2 meters. Now I have Vx still unknown, V naught y is unknown, and Ax, of course, is 0, Ay is equal to 0. Okay, so it looks like we still have enough information in the y direction to figure out time. And if you look at this, and you look back to part B, it's all the same information. Okay, all the same information in the y direction means the time should be the same. So we already automatically know t is 0.49 seconds. Okay, now that I know that, I'm going to put it into my x information, and I have xx equals x naught x plus v naught xt plus 1/2 ax t squared. Okay, of course, x naught x is 0, and 1/2, or ax is 0. So I have xx, which is 1.5, is equal to v naught x, which I want to know, times 0.49. Okay, I divide both sides by 0.49. And I solve for v naught x. I see that v naught x is equal to 3.06 meters per second. Okay, in part D, and hopefully write this down because I'm actually just going to erase this so I can keep the picture, and I'm going to write v naught x equals 3.06 up here in the corner. And so in part D, I want to know the y component of A's velocity after the collision. So what is A doing? I didn't even draw A in my picture. We can probably guess it's probably going off in the other direction. Maybe it's going to the left. We don't know. Okay. To do this, we can use sigma p naught y equals sigma p y. Okay, because nothing is happening in the y direction, and I'm making this my y and this my x. Nothing's happening in the y direction at the beginning, so the total y momentum is 0. Okay, at the end, we have m a v a y. Okay, but actually, that's just pay, the y component of of A's momentum, plus mc vcy is equal to 0. Okay, I know that my whole velocity, so I'm going to draw C's velocity triangle. The hypotenuse is 3.06 meters per second. I know that my angle right here is 30 degrees, and so VCY will be equal to 3.06 times sine 30. Okay, and you should remember from special triangles that the sine of 30 is equal to 1/2. So this is about 1.53. Okay, now I can go ahead and I can plug in numbers, but I'm not going to plug in the mass of ball V or the velocity of ball A. Okay, I'm not going to plug in the mass of ball A, or the velocity. So I have 0 equals pay plus the mass of ball C, which I know is 0.1, times 1.53, and it's going sort of downwards in my y direction, so that's negative. So I have pay is equal to 0.153, and I'm going to put my right units on it. It's kilograms times meters per second. All right, so hopefully you were able to do at least some of the parts of this problem. We're going to continue for the next couple of nights doing free response problems. Make sure that you're really trying them yourself first. Try to limit yourself in time and practice these, because this is, it's going to be very time pressured on the exam. See you guys tomorrow.